And welcome to today's lecture, April 8th, 2020, on sections 4.1 to 4.2, how derivatives affect the shape of graphs. So we'll talk about local versus absolute extrema and how derivatives affects the shape of graphs. Extrema here means a local or an absolute maxima or minimum. So first, a function has an absolute maximum at x equal to c if f of x is less than or equal to f of c for all x in the domain. F of c is called the absolute maximum value. Here's an example. The function f of x is 10 minus x squared. If you look at that, that's a parabola. It's facing downwards. It has an absolute maximum at x equal to 0, and the absolute maximum value is f of 0, which is 10, minus 0 squared, which is 10. 10 minus 0, anything minus 0 is itself. F of x has an absolute minimum value at x equal to c if for every number in the domain, the output value is larger than or equal to the output value evaluated at this value c. The value f of c is called the absolute minimum value of f of x. Here's an example. X minus 1 squared has an absolute minimum at x equal to 1. The absolute minimum value is f of 1, which is 1 minus 1 squared, which is 0 squared. And you can see this makes sense, right? X minus 1 squared, if you were to graph this, this would look like the graph of x squared, but shifted 1 unit to the right. And you can see for yourself, right, when anything in the parentheses is squared, any number, real number is squared, you always get a number that's larger than or equal to 0. It will be 0, though, when what's in the parentheses is equal to 0. That occurs when x is 1 and its minimum value is 0. If you plug in any other number, you're going to get an output value that is larger than 0. So that's what we mean by absolute maxima and minima. Let's talk about local maxima and minima. It's the same thing. But now we just care about what happens near x equal to c. So this means the top of a hill. As a local maximum, if f of c is larger than or equal to f of x for x near c. Has a local minimum at x equal to c if f of x is larger than or equal to c, f of c for x near c. That means the bottom of the valley. Here's an example. This function, this is the graph of a cubic function actually, and if you look at it, this has local maximum at this point. This green dot is local maximum. The x value is the local maximum. Is the place where local maximum occurs. It's the top of the hill. Go down to the bottom of the hill, you get a local minimum. This function, though, does not have an absolute maxima nor an absolute minima, right? Because for large x values that are large and negative, the output value is also large and negative. So the output value can be as negative as you want it to be, no minimum. And the output value can also be as large as you want it to be, no maximum. Here's what the first derivative tells us. F prime of x is larger than 0 on the interval from a to b. That means f is increasing. If f prime is less than 0 on a to b, f is decreasing. This should have said f is increasing on the interval from a to b. If f prime of c is 0, f prime of c does not exist, or f prime of c does not exist. C is called a critical number. C is for critical. If f prime is less than 0, or if x is less than 0, and f prime of x is larger than 0, for x larger than c, f prime of x changes from negative to positive at x equal to c, then f of x has a local minimum at x equal to c. So this means, right, if you were going to the bottom of the valley, what would you do? You would go down, and we'll see later on, f prime being negative corresponds to decreasing, and f prime being positive corresponds to increasing. If you go down from the top of the hill to the bottom of the valley, so your height is first decreasing, and then it's increasing. Height changes, equivalently, the derivative changes from negative to positive. If the derivative changes from positive to, that should have said positive to negative instead, this should have said f prime of x is less than 0. If f prime of x is larger than 0 for x less than c, and f prime of x is less than 0 for x larger than c, f prime changes from positive to negative at x equal to c. F is a local maximum. So that means f is changing from increasing. You're going, when you climb up a hill, right, your height is increasing to start. You reach the top, that's the local maximum, and then your height decreases as you go down the hill. That means f of x has a local maximum at x equal to c. The last two statements are called the first derivative test. Here's what the second derivative test tells us. F double prime of x is on, if it's positive, if the second derivative is positive on an interval, then the function, this was a mistake, this shouldn't have said f double prime, it should have said f of x is concave up on the interval. That means the curve, the graph of y is equal to f of x looks like a smile or equivalently a hill. If f double prime of x is less than 0 on a to b, then f double prime of x is concave down, means the curve looks like a valley or a frown. If f double prime of x is larger than 0 for x less than c, if for f prime of x is larger than 0 for x less than c, and f double prime of x is less, okay, that was a mistake. We'll get to in the next lecture local max, local min, but if f of x changes concavity, it has an inflection point at x equal to c. This means f double prime of x is less than 0 for x less than c, and f double prime of x is larger than 0 for x larger than c. Changes from concave down to concave up, or changes from concave up to concave down. F double prime is positive for x less than c, f double prime is negative for x larger than c. Now that we have those tools under our belt, what f prime tells us, what f double prime tells us, there are some steps for graphing y is equal to f of x. Step 1 is to differentiate the function, set the derivative equal to 0 to get all the critical numbers. Notice there also might be some critical numbers obtained from where f prime of x does not exist. Step 2 is to use the critical numbers to divide the domain into subintervals. Plug a test number into each of the subintervals into f prime of x. If f prime is positive, f of x is increasing on the subinterval. If f prime is negative, f is decreasing on the subinterval. Differentiating f again to get f double prime, and solve for f double prime of x is equal to 0. Use these solutions to divide the domain of f of x into subintervals, and plug a test number in each of these subintervals into f prime. If the second derivative is positive, we get concave up. If second derivative is negative, we get concave down. And again, that's going to hold on this entire subintervals. So we'll see when we get to examples. We're not going to have time in this lecture, but next lecture, we'll see that the critical numbers divide the domain of f of x into the number of critical numbers plus 1 subintervals, depending upon where, provided all the critical numbers live in the domain. And likewise, the number of solutions to f double prime of x is equal to 0, or where f double prime of x does not exist, will also divide the domain. Provided there are in the domain, they'll divide the domain into that number of solutions plus 1. Now, you might have noticed there are some possibilities here. There are intervals where f is increasing, f is decreasing, f is concave up, concave down. This corresponds, those possibilities, those 4 different possibilities corresponds to 4 different shapes of the graph. And these are basic shapes that you can use to sketch a curve of a graph. One is increasing concave up. This looks like this. You'll notice this is the exponential function. It's always concave up and increasing, but this could be the shape of part of your graph. The next basic shape is increasing but concave down. This is actually the logarithmic function that is graphed here. That's always concave, increasing, concave down, but this could be part of your graph. If on an interval your function is concave, increasing, concave down, this is what the shape of your graph is going to look like. The third shape is decreasing concave up. This is the function 1 over x, and this is a piece where the function is decreasing concave up. The fourth shape is decreasing concave down. This is actually another portion of the curve 1 over x. And there, that curve, same curve, is decreasing concave down. And you'll learn how to graph that curve, or really any function that you can differentiate and solve for the critical numbers just using the technique described above. So we'll get into some examples in Friday's lecture. All right.